Hello, today we're going to talk about solution energetics and we're going to do a brief review of molarity. All right, so basically when we have something dissolving in a solution, there's a couple of different factors that play into whether or not it will dissolve. So we know that not everything dissolves in water, for example. Some things are more soluble in water than others, right? And that's all related to how energetically favorable it is. And we'll get a lot more into what components those are and how they are factors when we get to our unit on thermodynamics. But we're going to do a brief overview today because it's important to understand, or it's necessary to understand how we can determine how soluble something is. Right. So if we are dissolving something in a liquid, in a solvent, right, the solvent molecules need to come apart and the solute molecules need to come apart. And then when they come back together, we form new interactions, okay? So to summarize all three of these processes, essentially, we use something called enthalpy of solution, which takes into account all of three of these. So it's basically the three added together. So the enthalpy of solution is how much heat is either released if delta H is negative or absorbed if delta H is positive when a solute dissolves in a solvent, okay? So generally, we favor forming interactions, and it takes energy, or we have to absorb energy if we're going to break interactions. So breaking apart our solvent molecules is going to have a positive delta H always. Breaking apart our solute molecules is always going to have a positive delta H. And then when we put them back together, we're going to form new interactions, so that's going to have a negative delta H. So you can see if two of them are always positive and one is negative, then the magnitudes of each of those is going to depend on whether or not it will dissolve or not dissolve. Okay, so we, in terms of the solute-solvent interactions, so how much energy we get back when we form new interactions, if that is bigger than the solvent, and solute interactions, so if the interactions we get here are stronger than the ones we had to break over here, then we will form a solution, okay? If they are equal, if the thing is a solid, which is what it was when we showed it on the previous slide, if our solute is a solid, then again, we will get solution formation. If, however, the solvent and the solute interactions are not as strong as the solvent and solute interactions together, then sometimes we get solution formation and sometimes we do not. So I wrote here that it depends. Okay, which is not a very satisfying answer, but that's the truth. It depends. So the reason it depends is because of something called entropy. All right, so entropy of solution formation is basically a measure of how dispersed our energy is in our system. Okay, so as things get more disordered, then our entropy goes up, and that will then So when we're dissolving a solid into a liquid, that entropy is always positive, which is what we want. And so that is enough to overcome any difference in the strength of the interactions like we just saw on the previous slide. Okay, so we're always looking at a balance between the enthalpy, which is the heat of solution, and the entropy, which is basically the spreading out of the energy in the system. Okay, so as temperature goes up, we favor the entropy even more. So as things get warmer, the system wants to disperse its energy more and more. So if you think about this in terms of kinetic molecular theory, as we warm things up, things move more. And if they're moving more, then the energy can be more dispersed. Okay, so that now means that we have a temperature dependence of our solubility. So for solids, when we have a solid and we dissolve it in a liquid, all right, so we're just talking about liquid solvents here. If we have a solid and we dissolve it in a liquid, there are many more ways now for that solid to move around because liquids have a lot more range of motion when they're moving. So for solids, as temperature goes up, our solubility will go up. Okay, for gases, it's the opposite. All right, so if you think about gas molecules being dissolved in a liquid, they can't move nearly as much when they're dissolved in that liquid as they could when they were in the gaseous phase. So for gases, as temperature goes up, our solubility actually goes down. And you've probably experienced that before. If you open like a can of soda that's warm, you can feel all those bubbles coming out on your tongue when you take a sip because they're not very soluble in the liquid anymore. Okay? Because our gas molecules also, their behavior is related to the pressure, we also, that pressure also influences their solubility. And so as our pressure goes up, we're squeezing those gas molecules together. And so then it's less of a change to go from a pretty compressed gas to a liquid. And so their solubility goes up as the pressure goes up. Okay. If you have like a soda stream, you probably know that, that CO2, you put it in when it's really high pressure, and that's what causes it to be able to go into the water that you're bubbling. All right. So now let's talk about just a review of concentration. So you should have learned about this in honors, but we basically have concentration is a way of telling us how much of a solute is dissolved in your solution. So a dilute solution has a little bit dissolved, and a concentrated solution would have a lot dissolved. These are just qualitative measures, so something can be more dilute than something else, but there's not like a number that's associated with this is dilute or this is concentrated, okay? But we do have a number associated with molarity. So there are many ways to express concentration, but molarity is the one we use most commonly. And the one that you're going to need to use most in this class. So molarity is the number of moles of a substance in 1 liter of solution. So that's 1 liter of total volume of solution and the number of moles that are dissolved in there. Okay, so let's do a couple of examples. All right, so how would you prepare a 1 molar solution of NaCl? All right, and this problem didn't give us a volume, so I'm just going to assume we're going to make 1 liter of it. All right, so if we're making 1 liter of this, 1 molar, which is how we say that capital M, it's molar. So 1 molar solution would be 1 mole dissolved in 1 liter of solution. And actually I should have more significant digits here. It should be 1.00 liters. Okay, so in order to know how to do that, we will make 1 liter of solution, so that will be our total volume at the end, but first we need to know how much solid we need to put in. So sodium chloride is a salt, it's a solid, and we can weigh that out on a balance. So we know from our periodic table that 1 mole of sodium chloride is the mass of sodium plus the mass of chlorine, so that's 58.44 grams. Okay, so now the steps to make this into a solution would include weighing out our grams of NaCl. So we're going to use an electronic balance to weigh out 1 mole. All right. Then we will put that into a volumetric flask. The volumetric flask is the best or most precise way to measure a total volume if that volume is like an even 1 liter or even 500 mils or something like that. All right. If you're measuring out, or if you're making a solution that's like, you need a total volume of 72 milliliters, you would need to use a graduated cylinder. But for the most part, we're going to use a volumetric flask. All right. You'll fill it part way with water. It doesn't matter exactly how much, just not all the way up. All right. And then you'll shake it up until everything is dissolved, and then fill it to the line. You want the meniscus to be just at that 1 line on the flask in order to get us exactly 1 liter of solution. Okay, and usually using a pipette to get that last little bit is good practice. It's hard to get it precise otherwise. All right, so one more example. This one is, what is the concentration of a solution that is prepared by dissolving 17.2 grams of ethylene glycol, and they give us the formula for ethylene glycol, in water and brought to a total volume of 515 milliliters, right? So we know that molarity is moles divided by liters, all right? So we have grams, which we could use to get moles, and we have milliliters, which we could use to get liters. Okay, so we're going to find each of those two values. So 17.2 grams of ethylene glycol, we can multiply by the conversion factor 1 mole over 62.07 grams. So this is the molar mass when we add up 2 carbons and 6 hydrogens and 2 oxygens. Okay, and when we do that math, we get 0.277 moles of ethylene glycol. So that's the top part of our equation. And then to get to liters, we do the 515 milliliters divided by 1,000 to get to liters, right? So we have 0.277 moles divided by 0.515 liters, and that gives us a molarity of 0.538 molar, okay? So remember that molarity, or that capital M, represents the number of moles in 1 liter. So we could also use this value as a conversion factor in dimensional analysis, similar to the way we just did here. When you have a volume of a solution, you can figure out how many moles you have.